Tonight, we're going to explore why it's impossible to find your way home in deep space. On Earth, this is easy. You use a compass, a map, or a phone pulling in a signal from satellites orbiting a few hundred miles above your head. Home is a fixed point. You can always find your way back. But take that same question and move it into deep space. Far beyond the orbit of Neptune, out past the edge of everything familiar, something strange happens. Home stops being a place. It becomes a moving target in a universe where nothing, not one single thing, is standing still. By the end of tonight, you're going to understand why an astronaut lost in deep space couldn't simply turn around and fly back, why every method that works close to Earth stops working the farther out you go, and why some of the smartest engineers in the world have spent decades trying to solve a problem that, at its core, may have no solution at all. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. Start with a simple question. Where is Earth right now? You might think the answer is obvious. Earth is where it always is. It's orbiting the Sun, 93 million miles away, tracing the same path it's traced for billions of years. But that answer is incomplete. It's missing almost everything that matters. Earth isn't just orbiting the Sun. It's spinning on its axis at over 1,000 miles per hour at the equator. It's circling the Sun at about 67,000 miles per hour. The entire solar system, Sun included, is orbiting the center of the Milky Way galaxy at roughly 500,000 miles per hour. And the Milky Way itself is moving through the local group of galaxies. It's drifting toward a structure astronomers call the Great Attractor at speeds exceeding 1 million miles per hour. Stack all of that together, and Earth is never in the same place twice. Not for 1 second. Not ever. Every position Earth occupies is temporary. It's gone, the instant it happens, replaced by a new position, a heartbeat, later. So, when someone says, home, what they actually mean is a location defined relative to other moving things. The Sun, the galaxy, the local group. Its coordinates built on top of coordinates, all of them shifting, none of them fixed. Here, on the surface, you never notice any of this. You wake up. The ground is where you left it. Your house hasn't moved. The mountains outside your window look exactly the same as they did yesterday. That's because everything around you is moving together. You, your house, the ground, the atmosphere, all of it is riding along together. Same speed, same direction, one connected system. Relative to each other, nothing has changed. But relative to the rest of the universe, you've traveled an almost incomprehensible distance since the last time you fell asleep. In one day, Earth moves about 1.6 million miles along its orbit around the Sun. In 1 year, the entire solar system, carried along by the Sun, travels more than 4 billion miles through the galaxy. None of that motion is something you can feel. None of it shows up if you look out your window. But it's real, and it matters enormously the moment you leave the bubble of things that are moving together with you. That's the first piece of the problem. Home isn't a fixed dot you can point a finger at. It's a location defined by a web of relationships, all of them constantly shifting. And once you're far enough away, that web stops being useful. It stops giving you anything to hold on to. Now think about what navigation actually requires. To find your way anywhere, you need at least one of two things: a fixed reference point you can measure your position against, or a very precise, unbroken record of every movement you've made since you started. On Earth, we have both in abundance. We have satellites in known, stable orbits. We have landmarks that don't move on human timescales. We have magnetic fields, star positions that are effectively fixed over a human lifetime, and radio towers broadcasting from known locations. Even far out in the solar system, we still have something close to a fixed reference: the Sun. Every planet, moon, and spacecraft in the solar system is orbiting that one dominant point of light. Its position, relative to distant stars, is well known and predictable. Spacecraft like Voyager and New Horizons navigate using something remarkably similar to how sailors once used the stars. Cameras on board the spacecraft photograph the positions of bright, well-catalogued stars. Software compares those positions to a stored map. Mission Control measures tiny shifts in angle between the spacecraft, the stars, and known objects like the Sun or nearby planets. From that, they can calculate exactly where the spacecraft is, sometimes to within a few miles, even when it's billions of miles from home. This works because, from a human timescale, stars appear frozen in the sky. Their true motion, called proper motion, is real. But it's so slow that it takes decades, sometimes centuries, to become noticeable at all. For navigation purposes, close to home, you can treat the stars as fixed. The math works out fine. But that trick, the one that makes almost all of modern spaceflight possible, has a limit. And once you cross that limit, everything changes. Here's the problem, in plain terms. Every method we use to figure out where a spacecraft is depends on comparing its position to something else. Another object, a star, a signal, a known distance. Close to Earth, we have an abundance of things to compare against. The deeper into space you travel, the fewer of those things remain useful. And the ones that do remain useful become less and less precise. Take radio tracking, one of the most powerful tools we have. NASA's Deep Space Network is a system of massive dish antennas spread across California, Spain, and Australia. It tracks spacecraft by sending a radio signal out, waiting for the spacecraft to send one back, and measuring exactly how long that round trip takes. Radio waves travel at the speed of light, and the speed of light is a known, fixed number. That means engineers can calculate distance with extraordinary precision just from the travel time. They can also measure the Doppler shift of the signal, the way its frequency stretches or compresses, depending on whether the spacecraft is moving toward Earth or away from it. That tells them velocity. Combine distance and velocity over time, and you get a remarkably accurate picture of where a spacecraft is and where it's heading. This is how we know, at almost any moment, exactly where Voyager 1 is. It's now more than 15 billion miles from Earth, drifting through interstellar space. But notice what this method depends on. It depends on Earth. It depends on a signal traveling back and forth between the spacecraft and a fixed set of antennas on our planet. And that dependency is exactly where the problem begins. The speed of light is fast, 186,000 miles per second. Fast enough that, for anything happening on Earth, it feels instantaneous. But space is big enough that even light starts to feel slow. A radio signal takes about 8 minutes to travel from Earth to the Sun's distance. It takes over 23 hours to reach Voyager 1, way out past the edge of the solar system. Send a message, and you wait nearly 2 days just to get a reply. Now, imagine a spacecraft, or a person, far beyond that. Not at the edge of the solar system, but genuinely out in interstellar space, years or decades away from home at any realistic travel speed. At that distance, the round-trip communication time isn't measured in hours. It's measured in years. Ask a question, and by the time the answer comes back, the situation you asked about may no longer exist. The spacecraft has moved. Its surroundings have changed. The advice from mission control is already outdated the moment it arrives. This is the first wall you hit when trying to navigate deep space. Earth cannot help you in real time. Every signal from home is a message from the past, describing a version of reality that no longer applies. You're not being guided. You're being informed, slowly, about where you used to be. So, if radio contact with Earth becomes useless for real-time navigation, what's left? The obvious answer is dead reckoning. Keep careful track of your speed, your direction, and how long you've been traveling. Then, calculate your position from that. Sailors did this for centuries before satellite navigation existed. It worked reasonably well for ocean voyages that lasted weeks or months. But dead reckoning has one fatal weakness. Errors compound. Every small mistake in measuring your speed, every tiny miscalculation in your heading, every unaccounted force acting on your ship gets added to the last one. The longer the journey, the larger the accumulated error becomes. On Earth's oceans, over a few weeks, that error might add up to a few miles. Annoying, but recoverable. Now stretch that same principle across a journey lasting decades, covering trillions of miles through an environment full of forces we can barely predict. Solar wind pushing unevenly against different parts of a spacecraft. Faint gravitational tugs from stars you're passing at enormous distances. Tiny thruster inefficiencies that never perfectly match their intended output. Micrometeorite impacts too small to detect, but large enough to nudge your trajectory by a fraction of a degree. None of these forces are individually significant. But dead reckoning has no way to correct for what it doesn't know it's missing. Over interstellar distances, even a rounding error measured in fractions of a degree can translate into a position error measured in millions of miles by the time you'd expect to arrive. A fraction of a degree, held constant over 4 light-years of travel, can shift your final position by a distance greater than the size of an entire star system. You wouldn't just miss your destination. You might sail straight past it without ever knowing it was there. So dead reckoning alone isn't enough. You need external references to correct your position along the way. And this is where deep space navigation runs into its second major wall. The stars, the ones we use so reliably near Earth, stop being reliable the farther and faster you travel. 2 separate problems appear at once. The first is called stellar aberration. If you're moving at a significant fraction of the speed of light, the apparent position of every star in the sky shifts. It's the same way rain appears to fall at an angle when you're running through it, even though the rain itself is falling straight down. The faster you move, the more dramatic this shift becomes. At even a modest fraction of light speed, the entire sky would appear to warp, with stars bunching up ahead of you and thinning out behind you. Every reference point your navigation system depends on would be displaced from where your charts say it should be. And the amount of displacement changes constantly as your own speed changes. The second problem is proper motion. The same slow drift of stars across the sky that we normally ignore because it's too small to matter on human timescales. Near Earth, over the length of a single space mission, this drift is irrelevant. but stretch a mission out over decades or centuries, and it stops being irrelevant. Stars you charted your course by, at the start of the journey, will have shifted, some by a small amount, some by a great deal, depending on their distance and true velocity through the galaxy. Your star map, the very thing your navigation depends on, becomes slowly, quietly, wrong the longer you're traveling. And there's a deeper issue hiding underneath both of these. Distance itself becomes hard to judge. Near Earth, we measure the distance to nearby stars using parallax, the tiny apparent shift in a star's position when viewed from two different points in Earth's orbit around the Sun. It's the same principle as holding a finger in front of your face and looking at it with one eye closed, then the other, and watching it appear to jump against the background. Parallax works beautifully for stars relatively close to us, within a few thousand light years. But the baseline we use to measure it, the width of Earth's orbit, is tiny compared to interstellar distances. The farther away a star is, the smaller its parallax shift becomes. Eventually, the shift is too small to measure at all, and the star simply appears fixed, regardless of its true distance. Now imagine you're not measuring parallax from Earth's orbit anymore. You're measuring it from a spacecraft moving through space at a fraction of light speed, with your own baseline constantly changing in ways that are difficult to calibrate. Every fixed point you thought you had becomes uncertain. Every star you use to check your position is itself shifting, both because it's genuinely moving through the galaxy and because your own motion is distorting how you perceive it. This is the deep irony of deep space navigation. The tools that work so well close to home, the stars, radio contact with Earth, dead reckoning, all begin to fail simultaneously the farther you go. Not because engineers were careless, but because those tools were never designed for the scale, speed, and duration that true interstellar travel would demand. So, what alternatives have scientists proposed? One of the most promising ideas is called pulsar navigation. Pulsars are the collapsed cores of massive stars that have exploded as supernovae. They spin incredibly fast, some rotating hundreds of times per second, sweeping a beam of radiation across space like a cosmic lighthouse. Certain pulsars, called millisecond pulsars, are remarkably stable, ticking with a regularity that rivals the best atomic clocks built on Earth. The idea is elegant. If you can detect the timing of pulses from several different pulsars scattered across the galaxy, and you know their positions and rotation periods precisely, you can calculate your own position in three-dimensional space. The method compares the exact timing of when each pulse arrives at your location. It works on a similar principle to GPS, except instead of satellites orbiting Earth, your beacons are collapsed stars scattered across thousands of light years, ticking with mechanical precision. NASA actually tested a version of this concept. Engineers flew an instrument on the International Space Station designed to detect X-ray pulses from several known pulsars and calculate the station's position using only those signals. It worked. The position calculated using pulsar timing matched the station's known orbital position to within a few miles. That's a genuinely remarkable achievement. It hints at a real, workable method for navigating far from Earth without needing constant radio contact. But pulsar navigation isn't a perfect solution either. The X-ray signals from distant pulsars are extraordinarily faint by the time they reach a detector. Picking them out clearly requires large, sensitive instruments and long observation times. A spacecraft moving quickly, needing frequent position updates, It can't necessarily afford to spend hours patiently listening for faint pulses from a handful of specific stars. Pulsar timing also has to account for the same relativistic effects, aberration, and time dilation that distort ordinary starlight. That means the calculations only get more complicated the faster you're traveling. And there's a longer-term issue too. Pulsars slow down gradually over time as they radiate away energy. Their timing, while remarkably stable over years and decades, isn't perfectly stable over centuries and millennia. Any navigation system built around pulsar timing would eventually need to be recalibrated using updated models of how each pulsar is slowing down, models that themselves carry small uncertainties. It's a powerful tool, genuinely one of the best ideas anyone has proposed for interstellar navigation. But it's not the flawless cosmic GPS system it's sometimes described as. It's another imperfect method layered on top of several other imperfect methods. And in deep space, that's often the best you can hope for. Now, let's talk about a problem that goes even deeper than instruments and calculations. A problem baked into the structure of space and time itself. If you were traveling fast enough to make an interstellar journey survivable within a human lifetime, you'd need to travel at a significant fraction of the speed of light. And at those speeds, time itself stops behaving the way it does in everyday life. This is time dilation, one of the strangest and best confirmed predictions of Einstein's theory of relativity. The faster you move relative to something else, the slower time passes for you relative to that other thing. At everyday speeds, on Earth, in cars and airplanes, this effect is so small it's meaningless. But at a significant fraction of light speed, it becomes dramatic. Travel at 90% of light speed, and for every year that passes for you on board your ship, more than 2 years pass back on Earth. Travel at 99% of light speed, and the ratio stretches even further, with roughly 7 years passing on Earth for every single year you experience. This means something unsettling. Even if you solved every navigational problem perfectly, even if you knew, with total precision, exactly where you were and exactly how to point your ship back toward the solar system, the place you'd be returning to would no longer be the place you left. Depending on how long and how fast your journey was, decades or even centuries could have passed on Earth by the time you made it back. The people you knew would be gone. The cities you remember would have changed beyond recognition, or might not exist at all in the form you remember. Coastlines shift. Governments rise and fall. Languages drift. Technology advances in ways impossible to predict from the deck of a departing spacecraft. In a very real sense, home wouldn't just be hard to find. It would no longer exist, not as the place you left. You could point your ship at the exact coordinates where Earth used to be relative to you, correct for its orbital motion, correct for the sun's motion through the galaxy, correct for every gravitational influence along the way. And you'd still arrive at a version of home that has nothing left in common with the one in your memory. This is perhaps the most unsettling part of the entire problem. Even a perfect navigational solution wouldn't be enough. Because the thing you're trying to return to isn't just a location. It's a location at a specific moment in time. And that moment is gone the instant you leave it behind. Let's step back and think about the scale involved, because numbers like these are almost impossible to feel intuitively. 4 light years, the distance to the nearest star beyond our sun, is roughly 25 trillion miles. If you were navigating toward a target that far away, even a tiny angular error at the start of your journey would translate into an enormous positional error by the time you arrived. An error of just 1 degree, held constant over that distance, would put you off course by more than 400 billion miles. That's not a small correction. That's missing your destination by a distance wider than our entire solar system. Now scale that thinking down to the problem of returning home. Your instruments, your star charts, your dead reckoning calculations, your pulsar timing, all of it could carry tiny individual errors. And if those errors compounded across years of travel, the region of space you'd actually need to search to relocate Earth could be staggeringly large. Not a few miles. Not a few thousand miles. Potentially, a search area larger than entire regions of the solar system, scattered across a volume of space so vast. Finding one small blue planet inside, it would be like trying to find a single grain of sand somewhere within an entire ocean, without knowing which ocean you're looking in. And remember, you wouldn't have real-time help from Earth to narrow that search. Every message sent to guide you home would already be years out of date by the time it reached you, describing a position Earth occupied long before you'd even received the correction. This is why, in any realistic discussion of deep space travel, the phrase "turning around and heading home" carries far more weight than it sounds like it should. It's not a simple maneuver. It's an entirely new navigational problem, arguably harder than the outbound journey. Because on the way out, at least, you're heading toward a destination that hasn't had time to drift very far from where your calculations expect it. On the way back, everything you're aiming for has kept moving the entire time you were gone. And your only information about where it's gone is old, uncertain, and getting staler by the day. There's also a more immediate, physical dimension to this problem that's easy to overlook. Human orientation itself depends heavily on visual and physical cues that simply don't exist in deep space the way they do on Earth, or even in low orbit. Astronauts on the International Space Station, despite being weightless, still have a nearby planet to look at, a horizon, sunrises and sunsets every 90 minutes, and constant radio contact with mission control, just a fraction of a second away. Deep space offers none of that. No up, no down, no nearby horizon, no passing landscape to judge your movement against. Stars, from a humanized perspective, all appear to sit at the same infinite distance, whether they're 4 light-years away or 40,000. Without instruments, a person floating in deep space would have absolutely no way to sense which direction they were moving, how fast, or whether they were moving at all. This isn't just uncomfortable. Historically, disorientation of this kind has proven to be one of the most psychologically taxing aspects of extended space travel, even on missions that never leave the safety of Earth orbit. Extend that disorientation across the true emptiness of interstellar space, where the ordinary cues your brain relies on for a sense of direction simply don't exist. It becomes clear why deep space navigation can't rely on instinct or observation the way navigation on Earth always has. Every scrap of positional awareness has to come from instruments, calculations, and models, filtered through imperfect data, corrected by imperfect assumptions, and never fully certain. Let's go back further, because the idea of a fixed point in space isn't just a modern engineering problem. It's a question physicists wrestled with for centuries. In the late 1800s, scientists believed the universe was filled with an invisible medium called the ether, a fixed background against which all motion could be measured. The idea made intuitive sense. Sound waves need air to travel through. Water waves need water. Light was known to behave like a wave, so surely it needed some kind of medium too, some universal backdrop that light waves rippled through. If that medium existed, then in theory, you could measure your speed against it, the same way you can measure your speed against the ground when you're walking. It would have been the ultimate fixed reference point, a cosmic ruler against which every motion in the universe could finally be measured. Two scientists set out to detect it. They built an incredibly sensitive instrument designed to measure tiny differences in the speed of light, depending on which direction it traveled relative to Earth's motion through this supposed ether. If the ether existed, light moving in the same direction as Earth's orbit should have measured slightly differently than light moving against it. The experiment was precise, repeated many times, refined again and again, and the result, again and again, was nothing. No difference at all. Light moved at exactly the same speed, no matter which direction it was measured in, no matter how Earth itself was moving through space. This result confused physicists for years, until a new explanation arrived that overturned the entire premise of the search. There was no ether. There was no fixed background. There was no universal frame of reference against which absolute motion could be measured, not for light, not for anything. Motion, it turned out, only makes sense relative to something else. There is no such thing as standing still in any absolute sense, only standing still relative to a particular object or observer. This idea, that the universe has no built-in fixed point, no cosmic zero on the map, isn't just an abstract piece of physics history. It's the deepest reason why finding your way home in deep space is so difficult. It's not simply that our instruments aren't good enough yet. It's that the universe itself was never built with an absolute reference frame in mind. Every position, every velocity, every direction only means something in relation to something else, and everything else is moving too. Now bring that same idea back down to something familiar, something almost everyone carries in their pocket. GPS. Global positioning works so well, so effortlessly, that most people never stop to think about how remarkable it actually is. A network of satellites orbits Earth at an altitude of about 12,000 miles. Each one carries an atomic clock precise enough to lose less than a second over roughly 3 million years. Each satellite constantly broadcasts its exact position and the exact time that signal was sent. Your phone or car receives signals from several of these satellites at once and measures the tiny difference in arrival time between them. It calculates its own position through a process called trilateration, essentially triangulating itself against several fixed, known points in the sky. It's an elegant system. It works because every part of it satisfies a condition that deep space simply doesn't offer. The satellites are close. Their positions are known with extreme precision at all times. There are enough of them visible from any point on Earth's surface to allow accurate triangulation. And crucially, the whole system operates within a communication delay measured in milliseconds, not hours or years. None of those conditions exist once you leave the solar system. There's no network of precisely known satellites surrounding you. There's no dense cluster of nearby, well-calibrated reference points broadcasting their position every fraction of a second. The stars that might serve a similar role are light years apart. Their signals take years to update, and as we've already seen, their apparent positions shift the faster and farther you travel. You could, in theory, imagine a future where humanity has placed a network of navigational beacons throughout nearby interstellar space, artificial satellites of a kind, broadcasting known positions, the way GPS satellites do. But building and maintaining such a network across light years of empty space is an enormous task on its own. Keeping every beacon precisely calibrated over centuries, and receiving their signals with usable speed and accuracy remains far beyond anything current technology could realistically achieve. For the foreseeable future, deep space travelers would have to rely on the universe's own imperfect landmarks and hope those landmarks are enough. There's another layer to this problem that rarely gets discussed. It involves something most people never think about: Earth's magnetic field. That field, generated deep within our planet's molten outer core, extends far beyond the surface, forming a protective bubble called the magnetosphere. It shields us from much of the sun's radiation. It's also been used for navigation for thousands of years, ever since the first compass was invented. But Earth's magnetic field, useful as it is, only extends so far. Beyond it lies the heliosphere, a much larger bubble carved out by the solar wind, a constant stream of charged particles flowing outward from the sun. The heliosphere extends roughly 11 billion miles from the sun, far beyond the orbit of Pluto. It acts as a kind of boundary between our solar system and true interstellar space. Voyager 1 crossed that boundary in 2012, becoming the first human-made object to leave the heliosphere and enter interstellar space directly. Once a spacecraft crosses that boundary, every trace of familiar, locally generated magnetic structure disappears. There's no compass to rely on, not even in principle. The interstellar magnetic field that exists out there is faint, complex, and shaped by forces entirely unrelated to our sun or our solar system. It offers nothing resembling the reliable, well-mapped magnetic field that guided sailors and pilots across Earth for centuries. Any spacecraft, or any future traveler, passing into that region loses yet another tool that worked reliably closer to home. Now consider the instruments spacecraft actually carry to measure their own motion directly, without relying on any external reference at all. These are called inertial measurement units. They work using gyroscopes and accelerometers that detect changes in orientation and velocity. In principle, if you know your exact starting position, and you can measure every single acceleration and rotation your spacecraft experiences afterward, you should be able to calculate your current position purely through internal measurement. No need to ever look outside. This is the purest form of dead reckoning. It's been used successfully for decades, guiding missiles, submarines, and early spacecraft with impressive accuracy over relatively short periods. The Apollo missions relied heavily on inertial navigation, with gyroscopes on board tracking the spacecraft's orientation throughout the journey to the moon. But even those systems required regular correction using star sightings because gyroscopes drift. Tiny imperfections in their construction, tiny amounts of friction, tiny sensitivity to temperature changes, all cause small errors to creep in over time. Those errors compound the same way dead reckoning errors compound at sea. For a 3-day trip to the moon, this drift was manageable, corrected periodically using precise star sightings taken through an onboard telescope. For a journey lasting decades, crossing trillions of miles, that same drift would become catastrophic. Even the most advanced modern gyroscopes, accurate to a tiny fraction of a degree per hour, would accumulate enough error over years of continuous operation to throw a spacecraft's calculated position off by an amount far too large to ignore. There is currently no gyroscope, no accelerometer, No inertial system built by humans capable of maintaining useful accuracy over the kind of timescale a true interstellar journey would require. Not without frequent correction from some kind of external reference. And we've already seen how difficult, how delayed, how uncertain those external references become the farther you travel. Just keeping our existing deep space missions on course already takes a tremendous amount of effort. It shows exactly how layered and constant this problem really is, even at distances that are, cosmically speaking, still extremely close to home. New Horizons, the spacecraft that gave us our first close look at Pluto, required several small trajectory correction maneuvers throughout its 9.5-year journey. Each one was calculated by teams on Earth using radio tracking data, then transmitted to the spacecraft as a precise sequence of thruster firings. New Horizons had all of Earth's tracking infrastructure, all of our accumulated knowledge of orbital mechanics, and clear, unbroken radio contact throughout the entire mission. It still needed constant, careful correction to arrive at its target with the precision required for useful science. And Pluto, despite feeling impossibly distant in our imagination, is only about 4.6 billion miles from Earth, at its farthest, a distance light crosses in a matter of hours. Scale that same need for constant correction up to a journey spanning light years, where correction signals take years rather than hours to arrive. The scope of the challenge becomes almost impossible to overstate. There's yet another subtle distortion that would confuse any traveler moving fast enough for relativity to matter. It involves color. As an object moves toward you, the light it emits shifts toward the blue end of the spectrum, a phenomenon called blue shift. As an object moves away, its light shifts toward red, called redshift. This effect, useful for measuring the motion of distant galaxies, becomes a significant complication for anyone traveling at a meaningful fraction of light speed. At those velocities, stars ahead of you appear shifted toward blue, sometimes dramatically, while stars behind you shift toward red. And the degree of that shift changes constantly as your own velocity changes. A star that should appear as a familiar, recognizable point of reddish or yellowish light might instead appear brilliant blue. Its true color completely disguised by your own speed relative to it. Identifying stars by their expected color, one of the ways astronomers catalog and recognize specific stars from great distances, becomes unreliable exactly when you'd need it most. At the highest speeds, during the most critical phases of a long journey. Every method of visual identification you might have relied on becomes distorted by the simple fact of moving fast enough to make the trip survivable in a human lifetime. There's also the environment itself to consider, quietly working against long-term precision the entire way. Interstellar space isn't a perfect vacuum. It contains sparse but real amounts of gas and dust, along with a steady bombardment of cosmic radiation. Those are high-energy particles that have been racing across the galaxy for millions of years, some of them originating from ancient supernova explosions. Over years and decades of exposure, this radiation can degrade sensitive electronics, slowly shifting the calibration of the very instruments a spacecraft depends on to measure its position and orientation. A star tracker that was accurate to a fraction of an arc-second at launch may drift slightly out of calibration after years of radiation exposure, introducing small, hard-to-detect errors into every position calculation it makes afterward. Dust particles, though incredibly sparse in interstellar space, still occasionally strike a spacecraft's surface. At a meaningful fraction of light speed, Even a microscopic particle carries enough energy to cause real damage, or at minimum, an unpredictable, tiny nudge to the spacecraft's trajectory. None of these effects are dramatic on their own. But navigation over interstellar distances isn't broken by one dramatic failure. It's eroded slowly by dozens of small, easily overlooked factors, each one adding a little more uncertainty to a picture that was never perfectly clear to begin with. Gravity adds its own quiet complexity as well. Every star a spacecraft passes near, even at a distance of many light years, exerts some small gravitational influence on its trajectory. Most of the time, this influence is negligible, far too small to matter for practical purposes. But over a journey spanning decades and trillions of miles, even negligible influences accumulate. They subtly bend a trajectory away from its originally calculated path in ways that are difficult to predict in advance. That's because they depend on the precise mass and position of every star along the route, many of which aren't known with perfect accuracy from Earth-based observation. Astronomers have catalogued the position and estimated mass of enormous numbers of stars. But small errors in those catalogues, multiplied across the length of an interstellar journey, add yet another layer of uncertainty to any attempt at precise long-term navigation. Compare this reality to how deep space is so often portrayed in film and fiction, and the contrast is striking. In most depictions, a lost astronaut simply looks out a window, spots a familiar constellation, and calculates a course home with a few taps on a console. Or a ship's computer instantly displays a glowing arrow pointing toward Earth, as though the universe came with its own built-in compass. The reality, as we've seen, is almost the exact opposite. There is no glowing arrow. There is no simple calculation. There is only a slow, careful, constantly revised estimate, built from imperfect tools, corrected whenever possible, and never entirely certain. Even our most advanced real spacecraft, tracked by the best instruments humanity has ever built, still require constant correction from a dedicated team on Earth, working around the clock. And that's simply to stay on course, across distances that are, on a cosmic scale, barely a first step beyond our own front door. There's one more piece of this puzzle, and it reaches into the strangest corners of physics itself. The very idea of right now doesn't mean what most people assume it means. Once you're dealing with objects separated by vast distances, because information, including light, can only travel so fast. Two observers moving at different speeds or separated by great distances don't necessarily agree on what's happening at the same moment. This isn't a limitation of our instruments. It's a fundamental feature of how space and time are woven together. For someone traveling at a significant fraction of light speed, deep in interstellar space, the very concept of Earth's current position becomes slippery in a way that has nothing to do with measurement error and everything to do with the structure of reality itself. There simply isn't a single, universally agreed upon answer to the question of where Earth is right now, once right now stops, meaning the same thing to every observer. It's a strange, almost dizzying idea, but it underscores just how deep this problem really goes. It's not solely an engineering challenge waiting for a clever enough solution. Part of it is woven into the basic physics of the universe, the same physics that once seemed to promise a fixed cosmic reference frame. Instead, it revealed that no such thing has ever existed. Let's go back to that pulsar navigation test for a moment, because the full details matter. The experiment flew on the International Space Station, using an instrument originally designed to study neutron stars for purely scientific reasons. Engineers realized that the same instrument, built to detect faint X-ray pulses from distant pulsars, could be repurposed as a navigation tool. They selected several millisecond pulsars, each one spinning with a rotation period known to extraordinary precision. Some complete hundreds of rotations every second, more consistent over time than almost anything else in nature. By carefully timing the arrival of pulses from 4 different pulsars and comparing the tiny differences in when each pulse reached the station, software on board calculated the station's position independently. No help from GPS or radio contact with the ground. The test succeeded, placing the station's position within a few miles of its known, verified orbit. And it did that entirely through starlight, from collapsed stars thousands of light years away. It was a genuine milestone, proof that a method resembling a natural, galaxy-scale GPS system is technically possible. But scaling that success up to a real interstellar mission introduces problems the orbital test never had to face. On the space station, the instrument had a stable, unmoving platform, plenty of time to gather data, and a known starting position to help calibrate its readings. A spacecraft racing through interstellar space at a meaningful fraction of light speed would have none of those luxuries. It would need to gather enough X-ray photons from faint, distant sources while moving, all while dealing with its own instrument, vibration, and accounting for its own extreme velocity, distorting the timing of every pulse it detects. Photon by photon, faint signals take real time to accumulate into a usable measurement. And a fast-moving spacecraft doesn't have the luxury of sitting still to listen. None of this makes pulsar navigation useless. It simply means it's one tool among several, powerful in principle, but still requiring significant advances before it could serve as a spacecraft's sole means of finding its way through the depths of interstellar space. Even a nearby crisis can test the limits of navigation. History already gave us a preview, much closer to home than deep space, but instructive all the same. During the Apollo 13 mission, an oxygen tank explosion crippled the spacecraft roughly 200,000 miles from Earth, forcing the crew to abandon their moon landing and fight simply to get home alive. With their primary navigation computer partially disabled to conserve power, the crew and mission control had to improvise a method to confirm the spacecraft's orientation. They used nothing more than the sun, visible through a window, lined up with a specific marking, cross-checked against known star positions. It worked. But it required extraordinary precision, calm nerves, and a huge amount of support from a team on Earth able to communicate with the crew in a matter of seconds. Running calculations on powerful computers and radioing instructions back almost instantly. Even then, close to home, with Earth clearly visible as a blue marble growing steadily larger in their window, with communication delays measured in mere seconds, the margin for error was razor thin. Now, imagine that same kind of crisis occurring not 200,000 miles from Earth, but 200,000 times farther, in the true emptiness of interstellar space. No blue marble growing larger in the window, no quick radio exchange with mission control, and no way to visually confirm your orientation against anything familiar at all. The tools that saved Apollo 13, a visible Earth, a visible sun, immediate radio contact, simply wouldn't exist. There's a particular piece of human history that captures this entire problem in a single poetic gesture. When Voyager 1 and Voyager 2 were launched, each carried a golden record. intended as a message to any civilization that might someday find it drifting through interstellar space. Etched onto the cover of that record is a map showing the position of our Sun relative to 14 specific pulsars. Each one is identified by its precise rotational period at the time of launch, encoded in a way intended to let a technologically advanced civilization calculate exactly where, and even roughly when, the spacecraft originated. It's essentially a cosmic return address, built using the very same pulsar timing principles that modern engineers are now trying to develop into a practical navigation system. The fact that scientists in the 1970s chose pulsars out of everything in the universe to mark our location says something important. Even then, they understood that ordinary landmarks, ordinary coordinates, mean nothing across such vast distances and such vast stretches of time. They needed something that would still make sense tens of thousands of years later, something durable enough to survive the drift of every closer, more familiar reference point. Pulsars were the closest thing available to a fixed address in an addressless universe. And even that address comes with an important caveat, one the Golden Record's designers were well aware of. Because pulsars slow down gradually as they age, the exact timing encoded on that record will very slowly become less accurate the farther into the future it's read. That means even humanity's carefully designed cosmic return address has a kind of expiration date, a slow drift toward inaccuracy, built into the physics of the very stars it depends on. Let's talk about the human side of this problem for a moment, because it's easy to get lost in instruments and equations and forget that a real journey like this would be experienced by real people. Researchers have studied isolation extensively, using environments on Earth that mimic some aspects of deep space, though none of them fully capture it. Submarine crews spending months underwater, cut off from regular contact with the outside world, have reported disorientation, difficulty tracking time, and a strange sense of detachment from familiar routines. Researchers stationed in Antarctica, through the long polar winter, isolated for months at a time, have described similar effects, along with measurable changes in mood, sleep, and cognitive performance. Even astronauts on the International Space Station, despite being just a few hundred miles from Earth, with a clear view of the planet and near constant contact with mission control, have described a persistent, subtle disconnection from ordinary human rhythms. Researchers sometimes call it space fog, a kind of mental haze that develops during extended time away from Earth's familiar cues. Every one of these environments still offers something deep space wouldn't. A horizon, however distant. A returning signal, however delayed. A planet, however small, visible somewhere in the sky. Strip all of that away completely, and you're left with an environment psychologically unlike anything humans have ever truly experienced. It's a darkness with no edges, no passing scenery, and no reliable way to sense your own motion through it at all. It's not hard to imagine how disorienting that would be, layered on top of every technical challenge we've already discussed. Let's go back to the numbers for a moment, because understanding the true scale of the search problem helps explain why this challenge is so much harder than it might first appear. Imagine a spacecraft returning from a journey 4 light-years out and 4 light-years back, an 8 light-year round trip, traveling at a significant fraction of light speed. Even with every navigational tool available, dead reckoning, star tracking, pulsar timing, all combined and cross-checked against each other, realistic estimates of accumulated positional uncertainty over such a journey could easily range from tens of millions to hundreds of millions of miles. That depends on how well each system performed and how many small, unaccounted forces nudged the spacecraft off its calculated path along the way. A search radius of even 10 million miles represents a volume of space enormous enough to contain thousands of Earth-sized planets with room to spare. All of it would need to be scanned, patiently, with instruments straining to detect a small, faint, reflective object against the overwhelming blackness of space. And that's assuming the uncertainty stays relatively small. Larger accumulated errors, especially over longer or faster journeys, could push that search radius into the hundreds of millions of miles. That's an area so vast that locating a single planet inside it without additional guidance could take years of careful searching, even once you were reasonably confident you were in the right general region of space. This is why any realistic vision of deep space return doesn't rely on visual searching alone. It relies on some combination of advanced radio broadcasts, agreed rendezvous coordinates, calculated and recalculated over years, and enormous reserves of patience. None of which changes the underlying truth. Home, once you've left it far enough behind, becomes something you have to painstakingly relocate, not something you can simply see and steer toward. Scientists have proposed a number of ideas that might someday close this gap, though all of them remain firmly in the realm of future technology rather than present capability. One idea involves networks of powerful lasers positioned throughout the solar system or even beyond it. They'd be capable of sending extremely precise, tightly focused beams of light to a returning spacecraft, allowing far more accurate ranging and timing than radio signals alone can currently provide. Another involves deploying small, long-lived beacon satellites at key points along likely interstellar travel routes, essentially planting artificial lighthouses at chosen locations to serve as intermediate reference points. That would reduce the enormous gap between departure and destination into a series of shorter, more manageable legs. A third idea, still largely theoretical, involves quantum sensors capable of measuring motion and rotation with a precision far beyond what today's gyroscopes and accelerometers can achieve, potentially reducing the rate at which dead reckoning errors accumulate over long journeys. None of these ideas are ready today. Each one faces enormous engineering, financial, and physical hurdles before it could become a practical part of any real mission. But together, they represent the general direction serious researchers believe this problem will eventually need to be solved. Not through a single breakthrough, but through several complementary systems working together, each one covering for the weaknesses of the others. There's also a broader, quieter consideration, one that applies specifically to any journey long enough to stretch across multiple human generations. If a voyage into deep space lasted so long that the people who eventually attempted to return were the descendants, not the original travelers, the very idea of home might mean something entirely different to them than it did to the people who first left. Culture drifts. Memory fades. Stories passed down through generations change, with each retelling. A crew, born and raised entirely aboard a ship, having never seen Earth, having only heard about it through inherited stories and preserved records, might not experience the pull of home the same way their ancestors did. The navigational problem would remain exactly as difficult. But the emotional weight behind solving it, the urgency, the longing, might fade along with everything else that gets lost across so many generations spent adrift. It's a strange thought, but it fits naturally into everything else we've covered tonight. Distance in space, doesn't just separate people from a place. Over long enough timescales, it can separate people from the very meaning that place once held. One final piece of context helps tie all of this together. It involves how astronomers actually build the star catalogues that spacecraft rely on in the first place. A space telescope named Gaia, launched by the European Space Agency, spent years precisely measuring the positions, distances, and motions of nearly 2 billion stars across the galaxy. It produced, by far, the most accurate map of the night sky ever created. That map is what makes modern star tracking possible at all. And each new release of Gaia's data has steadily improved the precision available to spacecraft navigation systems. But even a map that detailed and that carefully measured is, by necessity, a snapshot, a single moment frozen in an ever-changing sky. Every star in that catalogue continues moving after the measurement is taken, and the catalogue itself has to be periodically updated to stay useful, especially for missions expected to operate far into the future. For a mission lasting a few years, this isn't a major concern. For a hypothetical mission lasting decades or centuries, even the finest star catalogue ever produced would need to be treated as a starting point, not a permanent, unchanging truth. It's one more piece of the layered, imperfect system that deep space navigation ultimately depends on. There's an entirely different category of proposed interstellar mission worth considering here, because it faces this same problem in an even more extreme form. Several research groups have proposed sending tiny spacecraft, some no larger than a postage stamp, attached to ultra-thin sails, pushed to a meaningful fraction of light speed using powerful ground-based lasers. The appeal is obvious. A spacecraft that light needs far less propellant can be accelerated far more easily and could theoretically reach a nearby star system in a couple of decades rather than centuries. But a spacecraft that small comes with a brutal trade-off. There's almost no room for the heavy, power-hungry instruments that larger missions use for navigation. No large star tracker cameras. No powerful transmitter capable of sending a strong signal back across light years. No room for a pulsar timing instrument sensitive enough to gather usable data. These tiny probes are largely designed to be one-way messengers. They gather what data they can during a brief, high-speed flyby of a target star system, then transmit whatever they've collected back toward Earth using a faint, tightly focused signal, hoping it's strong enough to be detected across such an enormous distance. The idea of such a probe ever navigating its way back to Earth isn't really part of the design at all. It's simply too small, too fast, and too limited to carry the kind of navigational package a return journey would require. For missions like these, the entire challenge of finding your way home doesn't just get harder. It gets set aside almost entirely, replaced by a different goal, sending information home rather than bringing the spacecraft itself back. Generation ships and other large crewed concepts for interstellar travel face the opposite problem. They're big enough to carry sophisticated navigation equipment, potentially even redundant systems, multiple star trackers, backup gyroscopes, dedicated instruments for pulsar timing. But their journeys are so much longer, stretching across decades or centuries. Even the best instruments face the accumulated drift, radiation damage, and calibration decay we've already discussed, compounded further by needing to remain functional and accurate for far longer than any spacecraft humanity has ever built and operated continuously. A probe only needs to stay accurately navigated for a matter of years. A generation ship would need every part of its navigation system, and the humans responsible for maintaining and interpreting it, to remain reliable across a span of time longer than most technologies in human history have ever remained in continuous, dependable use. Every navigational challenge we've discussed tonight would need to be solved, not once, but repeatedly, generation after generation, and it would be solved by crew members who may never fully trust instruments built by engineers who lived and worked centuries before they were even born. Let's spend a little more time with the strangest consequence of high-speed travel. Picture two people, identical in every way, one staying on Earth, the other boarding a spacecraft capable of reaching a significant fraction of light speed. The traveling twin heads out toward a distant star, spends some time there, then turns around and heads back. From the perspective of the twin who stayed behind, the entire round trip might take, say, 10 years. But from the perspective of the twin who made the journey, because of how time dilation works at high speed, only a few years might have passed on board the ship. When the traveling twin finally returns, they step off the spacecraft younger, in a very real, physically measurable sense, than the twin who never left. This isn't science fiction. It's been directly measured, in smaller, far less dramatic form, using precise atomic clocks flown on airplanes, and compared to identical clocks left on the ground. That confirmed that time genuinely does pass at different rates, depending on relative speed. Scale that same effect up to the speeds required for interstellar travel, and the difference stops being a fraction of a second. It becomes years, potentially decades, depending on how fast and how far the journey goes. This is why the challenge of finding your way home in deep space isn't only about spatial coordinates. It's about time as well. Even a perfectly calculated position, matched exactly to where Earth will be when you arrive, still delivers you into an Earth that has aged years beyond what you experienced during your own journey. You're not just navigating through space. You're navigating into a future version of home that you never got to watch unfold, arriving as a kind of visitor from the past, disconnected from everything that happened while you were away. Now, let's zoom out to a scale even larger than an individual journey, because home itself is embedded in motion at every level, all the way up. Our Sun, carrying Earth and the rest of the solar system along with it, orbits the center of the Milky Way galaxy roughly once every 230 million years. At the heart of that orbit sits a supermassive black hole, a region of intensely warped space-time known as Sagittarius A, around which the entire galaxy slowly rotates. The last time our solar system completed one full lap around that distant galactic center, there were no flowering plants on Earth, no birds, no mammals, resembling anything alive today. We are, right now, only a small fraction of the way through our current orbit around the center of our own galaxy. This means that even the broadest possible definition of home, our solar system's place within the Milky Way, is itself slowly sweeping through an enormous, multi-hundred-million-year circuit. It's carrying everything and everyone along with it, whether we notice or not. Zoom out even further, and the picture becomes stranger still. Space itself, the very fabric that distances are measured across, is expanding, stretching gradually in every direction. That causes distant galaxies to drift apart from each other over time. This expansion is negligible at the scale of a single galaxy, far too small to affect anything happening within the Milky Way itself. So it doesn't complicate a hypothetical trip to a nearby star in any meaningful way. But it's a reminder of just how many layers of motion are stacked on top of each other, from a planet spinning, to a solar system orbiting a galactic center, to galaxies drifting apart across the largest scales imaginable. Nothing in this universe, at any scale, holds still. Home was never a fixed dot. It was always a point riding along inside a nested series of enormous, ongoing movements. Deep space simply removes the illusion that let us ignore that fact. The tracking system that keeps our actual spacecraft found shows just how much infrastructure is required, even for missions that never leave the solar system. NASA's Deep Space Network relies on 3 complexes spaced roughly 1/3 of the way around the globe from each other, one in California, one in Spain, and one in Australia. This spacing isn't accidental. As Earth rotates, at least one of these complexes is always facing whichever direction a distant spacecraft happens to be, allowing continuous contact as our planet spins underneath the sky. Each complex uses massive dish antennas, some over 200 feet across, capable of detecting radio signals from spacecraft so faint you'd hardly believe it. The total power received from something like Voyager, after traveling billions of miles, measures in fractions of a billionth of a watt. To put that in perspective, the signal arriving from Voyager 1 is so weak that the combined power collected from it across an entire year of listening wouldn't be enough to power a single small light bulb for even a fraction of a second. Detecting a signal that faint requires extraordinarily sensitive receivers, careful filtering of background noise, and enormous antennas working in precise coordination. Now imagine trying to build and maintain a similar tracking capability for a mission traveling not billions of miles, but tens of trillions of miles. The signal would have grown fainter still, spread across a return trip lasting decades, using technology that would need to remain operational and precisely calibrated the entire time. Every part of the system that currently makes deep space tracking possible would need to be pushed dramatically beyond its current limits, not through one breakthrough, but through years of incremental advances in antenna sensitivity, signal processing, and long-term reliability. Picture, for a moment, what an actual multi-decade solo journey into deep space might genuinely feel like, stripped of any dramatic embellishment, based only on what we've covered tonight. Weeks after leaving the solar system, the sun itself would begin shrinking into just another point of light among the stars. No longer a disk, no longer something that provides warmth or a clear sense of direction, just one more distant light among thousands of others. Communications with Earth would grow slower and slower. Each message, a fading transmission from a version of home growing further out of reach with every passing year. Instruments would require constant, careful monitoring, cross-checking star positions against onboard catalogs, watching for the subtle signs of gyroscope drift, waiting patiently for faint pulsar signals to accumulate into something usable. Every calculation would carry with it a small, honest acknowledgement of uncertainty, a margin of error that grows a little wider with each passing month, never quite resolving into the kind of confident, simple certainty that a compass or a road sign offers here on Earth. And at the far end of that journey, whenever the decision came to turn around, the destination waiting at the other end wouldn't simply be Earth. It would be an Earth that had kept moving, kept aging, kept changing in ways impossible to know from so far away, for the entire time its traveler had been gone. There's a technique engineers use today to pin down a spacecraft's position with even greater precision than simple round-trip timing allows. It shows both how clever and how fundamentally Earth-dependent our current methods really are. It's called very long baseline interferometry. Instead of relying on just one antenna, engineers use 2 or 3 widely separated dishes, sometimes on different continents, to receive the same signal from a distant spacecraft at very slightly different times. That's because the signal has to travel a tiny bit farther to reach one antenna than another. Engineers measure that tiny timing difference with extreme precision and compare it against the known, fixed distance between the antennas themselves. That lets them calculate the spacecraft's direction in the sky with remarkable accuracy, far better than a single antenna could achieve alone. Combined with the distance measurement from simple round-trip radio timing, this gives mission control an extremely precise, three-dimensional fix on a spacecraft's true position. It's an elegant technique. It's part of why we can track something as small and as far away as Voyager 1 with such confidence. But notice, once again, what this method fundamentally depends on. It depends on multiple fixed antennas here on Earth, precisely surveyed, precisely synchronized, working together as a single enormous instrument. Move the spacecraft far enough away and stretch the communication delay out to years instead of hours. This technique stops being useful for real-time navigation, the same way every other Earth-based method does. It remains an excellent way to know, after the fact, exactly where a distant spacecraft was at a given moment. It's far less useful as a tool a traveler could rely on to steer decisions of their own, in real time, far from home. Timing itself introduces yet another quiet complication, because every navigation method we've discussed depends on extremely precise clocks. And clocks, even the best ones humans have ever built, aren't perfectly immune to drift. Atomic clocks, the most accurate timekeeping devices ever created, measure time using the extremely consistent vibrations of atoms, typically cesium or rubidium. They're accurate enough that the best examples would lose less than a single second over hundreds of millions of years. That sounds essentially perfect, and for almost every practical purpose, it is. But a spacecraft's onboard clock and the clocks used by tracking stations on Earth aren't physically the same device. They have to be synchronized, periodically, using signals sent back and forth. And any tiny mismatch between them translates directly into a tiny error in every distance calculation that depends on precise timing. Over short missions, this effect is negligible, far smaller than other sources of error. But relativity adds an extra twist here too. A clock moving at high speed relative to another clock genuinely ticks at a different rate, not due to any mechanical imperfection, but due to the same time dilation effect that separates the ages of our two hypothetical twins. A clock on board a spacecraft traveling at a meaningful fraction of light speed would need to be continuously, carefully adjusted to stay meaningfully synchronized with clocks back on Earth. And any small error in that adjustment would ripple outward into every position, a calculation the mission depends on. There's also a very practical, unglamorous limitation sitting underneath all of this. One that has nothing to do with instruments or physics, and everything to do with basic engineering reality. Fuel. Every correction to a spacecraft's trajectory, however small, requires firing thrusters. And every thruster firing consumes propellant that can never be replaced once a mission leaves Earth. Mission planners have to balance accuracy against conservation, correcting course often enough to stay on target, but not so often that they exhaust their limited fuel supply long before the journey is complete. For missions within the solar system, this balance is manageable, refined over decades of practical experience. For a journey lasting years or decades across interstellar distances, this balance becomes far more delicate. Every correction burns propellant that a returning traveler might desperately need later, especially if unexpected drift, unexpected gravitational nudges, or unexpected instrument errors require larger, more urgent corrections near the end of an already fuel-depleted journey. In principle, you could carry more fuel to allow for more corrections. In practice, more fuel means more mass. And more mass means needing even more fuel just to accelerate that extra weight in the first place. A compounding trade-off that engineers call the tyranny of the rocket equation, one of the most stubborn, unavoidable constraints in all of spaceflight. Contrast all of this with how human navigators actually succeeded for thousands of years without any of our modern instruments at all. The comparison highlights exactly what's missing once you leave Earth behind. Polynesian navigators, sailing across the vast Pacific Ocean, centuries before written charts or compasses reached the region, developed an extraordinarily sophisticated system of wayfinding. They used the rising and setting points of specific stars along the horizon, the direction and pattern of ocean swells, the behavior of seabirds, and the color of the sky to guide voyages across thousands of miles of open water with remarkable accuracy. It was, and remains, one of the most impressive navigational achievements in human history, built entirely on close, patient observation of a consistent, repeating environment. But notice what made it work. The stars they used rose and set in predictable, repeating patterns because Earth itself was rotating steadily beneath a sky that, for practical human purposes, held still. The ocean swells they read were generated by predictable nearby weather patterns and coastlines. The birds they tracked were returning to islands that stayed exactly where they'd always been. Every tool available to those navigators depended on a stable, repeating, nearby environment, exactly the kind of environment that simply doesn't exist once you leave the solar system behind. Deep space offers no repeating horizon, no consistent nearby landmarks, no seabirds returning to a fixed island. It offers only distant points of light, shifting subtly with your own velocity, and an unforgiving, unblinking silence in every direction. The very ingenuity that let ancient sailors conquer the largest ocean on Earth simply has nothing to work with once the environment itself stops holding still. Given how many of these problems stem from the delay in getting help from Earth, some researchers have proposed a different approach entirely, shifting more of the navigational decision-making onto the spacecraft itself. Rather than waiting years for instructions from mission control, an autonomous system, using onboard artificial intelligence, could theoretically analyze star tracker data, pulsar timing, and accumulated dead reckoning estimates. Then it could make its own real-time decisions about small course corrections without waiting for confirmation from Earth at all. Early versions of this kind of autonomous navigation have already been tested on missions much closer to home, including spacecraft capable of identifying comets or asteroids and adjusting their own trajectory slightly, without step-by-step human instruction. Extending that same independence to a true interstellar mission is an appealing idea because it removes the crippling communication delay from the decision-making loop entirely. But it doesn't remove the underlying uncertainty. An onboard AI system would still be working with the exact same imperfect inputs: drifting gyroscopes, shifting starlight, faint and inconsistent pulsar signals that we've already discussed at length. Removing Earth from the loop makes decisions faster. It doesn't make the underlying information any more accurate. In some ways, it simply shifts the burden of navigating an inherently uncertain universe from a team of engineers on Earth to a computer system millions or billions of miles away, still working with the same fundamentally imperfect tools. There's one more version of this problem worth considering, because it strips away Earth entirely and asks a slightly different question. Imagine two separate spacecraft, both traveling through deep space, both wanting to find each other and meet at some agreed location. Neither one has a fixed point to measure against. Both are moving, and both carry their own small, accumulating navigational errors. Both are trying to calculate not just their own position, but the position of another object that's equally uncertain about where it is. This is, in a sense, the purest version of the entire problem we've explored tonight, stripped of the comforting idea that at least one side of the equation, Earth, might hold reasonably still. Two moving, uncertain points, trying to locate each other across an empty, referenceless expanse, is a problem that shows up in different forms throughout robotics and navigation research. It only gets harder as the distances involved grow larger and the available reference points grow sparser. It's a small, elegant illustration of just how much of ordinary navigation quietly depends on having at least one thing that isn't moving relative to everything else, and how rare that condition becomes once you're truly out among the stars. It helps to think of this entire problem as a gradient, rather than a single line that's either crossed or not, because difficulty increases steadily the farther you travel, long before you ever reach true interstellar space. Navigating to the moon, 250,000 miles away, is manageable with communication delays measured in a couple of seconds. Earth remains a bright, unmistakable reference point the entire way. Navigating to Mars, tens of millions of miles away depending on the alignment of the two planets, stretches communication delays out to between roughly 4 and 24 minutes one way. Mission controllers can no longer react instantly, but they can still send meaningful corrections within the same day. Spacecraft heading toward Mars already have to rely heavily on pre-calculated trajectories and onboard systems capable of handling short-term decisions independently. A small preview of the independence a true interstellar mission would need on a much larger scale. Navigating to the outer planets, Jupiter, Saturn, and beyond, stretches those delays to tens of minutes or even hours. Earth itself begins shrinking into just another point of light rather than a clearly visible disk. Navigating to the edge of the solar system, where Voyager currently travels, stretches communication delays to nearly a full day for a single round trip. Earth becomes indistinguishable from the background stars without instruments specifically designed to locate it. Interstellar space simply continues that same trend to its logical, extreme conclusion. Communication delays stretch from days into years, and Earth's visibility fades from a faint point of light into something requiring careful calculation just to know where to look at all. Every single challenge we've discussed tonight already exists, in smaller form, within our own solar system. Interstellar travel doesn't introduce a fundamentally new kind of problem. It simply removes every remaining safety margin that makes those same problems manageable closer to home. Signal strength itself follows an unforgiving mathematical rule that makes this gradient even steeper than distance alone would suggest. Radio signals, like light, spread out in every direction as they travel, weakening according to what's called the inverse square law. That means if you double the distance a signal travels, its strength drops to 1/4 of what it was, not half. Triple the distance, and strength drops to 1/9. This is why the faint whisper of a signal from Voyager, already billions of miles away, requires some of the most sensitive receiving equipment ever built just to detect at all. Push that same signal out to the kind of distances involved in true interstellar travel, tens of trillions of miles instead of billions, and the mathematics becomes almost absurd. A signal that weak, spread across a distance thousands of times greater than Voyager's current range, would require either an enormously more powerful transmitter than any spacecraft could realistically carry, or a receiving antenna on Earth so large it would dwarf anything currently in existence. That's all just to pull a usable signal out of the background noise of the universe. This is part of why any realistic interstellar mission concept assumes communication will become sparser and sparser the farther a spacecraft travels. Not because engineers choose to communicate less often, but because physics itself makes frequent, detailed communication increasingly and eventually completely impractical. There's an interesting parallel to all of this that runs in the opposite direction, one that involves humanity trying to be found, rather than trying to find its way home. In 1974, scientists used the massive radio telescope at Arecibo in Puerto Rico to broadcast a deliberately designed message toward a distant cluster of stars. It encoded basic information about humanity, our numbers, our chemistry, our solar system, using a simple sequence of radio pulses that any sufficiently advanced civilization might be able to decode. The message was sent toward a target roughly 25,000 light-years away. Even if it's eventually received and understood, and even if a response was sent back immediately, the entire round trip would take 50,000 years. That message represents, in its own way, the flip side of the exact problem we've spent tonight exploring. If humanity ever wanted to be found, ever wanted some future traveler, human or otherwise, to know where home is located, we'd face the same fundamental obstacle, trying to communicate a fixed address across a universe where nothing holds still long enough to have one. The Arecibo message, like the golden records aboard the Voyager spacecraft, had to rely on the same imperfect solution we've returned to again and again tonight: pulsar positions, relative rather than absolute coordinates, an approximate address built from the least unreliable landmarks the universe happens to offer. Let's pull every thread we've followed tonight together into one place, because taken individually, each piece might seem like a solvable engineering hurdle. Dead reckoning drifts, accumulating small errors into large ones over years of travel. Star tracking distorts as stellar aberration and genuine proper motion shift the very reference points a spacecraft depends on. Radio contact with Earth becomes a conversation with the past, arriving too late to offer real-time guidance across true interstellar distances. Pulsar navigation, while promising, requires long observation times and remains vulnerable to the same relativistic distortions affecting everything else. Magnetic navigation disappears entirely beyond the heliosphere, leaving no compass of any kind to fall back on. Inertial instruments, gyroscopes, and accelerometers drift steadily over time, with no interstellar mission yet capable of correcting that drift over decades without external help. Radiation and dust slowly degrade the very sensors a mission depends on, introducing small errors that compound the longer a journey lasts. Gravitational influences from passing stars subtly bend a trajectory away from its calculated path, in ways that are difficult to predict with complete accuracy in advance. Fuel constraints limit how often and how significantly a spacecraft can correct its course, forcing a delicate, unforgiving balance between accuracy and conservation. And underneath every one of these individual problems sits the deepest issue of all, the simple, well-established fact that the universe contains no fixed, absolute reference point for anything to measure itself against in the first place. Each of these problems, on its own, might be manageable. Engineers are resourceful. History has shown, again and again, that individual technical obstacles tend to yield eventually to patient, incremental progress. But navigating home from deep space isn't one problem. It's all of these problems, stacked together, compounding simultaneously, over a timescale and a distance that pushes every one of them to its absolute limit at the same time. There's a visual effect tied to high-speed travel that adds one more layer of distortion on top of everything already discussed. At a significant fraction of light speed, light itself doesn't just shift in color. It also appears to concentrate, brightening dramatically in the direction of travel while fading in the direction you've come from. An effect sometimes called relativistic beaming. Stars scattered evenly across the sky before departure would begin to visually crowd toward the forward direction as speed increased, growing brighter and more tightly clustered directly ahead. The sky behind would grow dimmer and sparser until, at extreme enough speeds, it would appear almost completely dark. This means the sky itself, the entire visual backdrop a traveler might instinctively rely on for a rough sense of orientation, would look nothing like the sky charted before launch. It's distorted, not randomly, but in a precise, predictable, yet deeply unfamiliar way tied directly to the ship's own velocity. Any instrument, or any person, attempting to judge direction simply by looking at the pattern of stars would be working with a sky actively reshaped by their own motion through it. One more example of how the observer's own speed becomes tangled up with the very thing they're trying to measure. Given how many independent sources of error we've covered tonight, engineers manage that uncertainty in practice by never trusting any single method completely. It's redundancy. Real spacecraft navigation, even for missions well within the solar system, rarely relies on just one technique. Dead reckoning estimates are constantly cross-checked against star tracker readings. Star tracker readings are cross-checked against radio ranging from Earth whenever contact is available. Any available pulsar timing data, however sparse, gets folded in as an additional, independent check against the others. When two or more independent methods agree closely, confidence in the calculated position goes up. When they disagree, engineers know something is wrong, even if they can't always immediately tell which system is at fault. That disagreement itself becomes valuable information, prompting a more careful investigation rather than blind trust in any single readout. This layered, cross-checking approach is, in many ways, the most honest solution humanity currently has to the entire problem explored tonight. Not a single perfect answer, but a patchwork of imperfect methods, each one covering for the blind spots of the others, constantly compared against each other to catch mistakes before they compound into something dangerous. It's not elegant. It's not the simple glowing arrow that fiction imagines. But it's resilient, in the same way a chain made of several slightly weak links can still hold, as long as enough of those links happen to be strong at any given moment. There's a physical, bodily dimension to disorientation in deep space that goes beyond simply lacking visual landmarks. It involves the inner ear. Human balance relies heavily on a small, fluid-filled structure inside the ear called the vestibular system, which detects motion and orientation relative to gravity. In the weightlessness of orbital spaceflight, astronauts commonly experience a period of adjustment as their vestibular system, receiving no clear gravitational signal, struggles to reconcile what it senses with what their eyes are telling them. That often results in disorientation and motion sickness during the first several days of a mission. Over time, most astronauts adapt, learning to rely more heavily on visual cues to compensate for the inner ear's confusion. But that adaptation still depends on having reliable visual cues available, a clear sense of up and down established by the layout of a spacecraft's interior, familiar visual references through a window. In deep space, far from any nearby planet, moving at extreme speed through a visually distorted sky, even those compensating visual cues become unreliable. That leaves both the inner ear and the eyes struggling to agree on any stable sense of orientation at all. It's a small, easily overlooked detail, but it illustrates just how much of ordinary human navigation, even the most basic sense of which way is up, depends on cues that simply don't exist once you're far enough from anything familiar. Given everything we've covered tonight, there's one more idea that quietly sidesteps the entire problem rather than solving it. Some mission concepts, particularly those involving generation ships or other extremely long-duration voyages, aren't designed around the idea of returning at all. They're designed for one-way settlement, carrying people toward a new home rather than attempting the far more complicated, far riskier return journey. In a strange way, this approach avoids nearly everything we've discussed tonight, not by solving the navigational challenge of finding your way back, but by removing the need to ever attempt it in the first place. There would still be enormous challenges in accurately reaching a chosen destination the first time. All the difficulties of dead reckoning, star tracking, and long-term instrument drift still apply on the outbound leg. But at least there would be no return trip demanding a second, even more uncertain calculation. No attempt to relocate a home that has spent decades or centuries drifting further from where it once was. It's a pragmatic, if sobering, way of acknowledging just how difficult the return half of this problem really is. Sometimes, the most realistic answer to an almost impossible challenge isn't a clever new technology. It's choosing not to attempt the hardest part of the journey at all. There's a well-documented psychological phenomenon that astronauts have described after seeing Earth from space. Researchers call it the overview effect, a profound shift in perspective that comes from watching our planet hang alone against the blackness. It's a small, fragile, borderless sphere with no visible lines separating countries, no visible evidence of the conflicts and divisions that seem so significant from the surface. Astronauts who've experienced this consistently describe a deepened sense of Earth's fragility and a stronger emotional connection to it as a single, unified home, rather than a collection of separate places. That experience depends heavily on something we've spent this entire exploration establishing. Doesn't exist in true deep space, a visible, nearby Earth to look back at. Every astronaut who has described the overview effect experienced it from orbit, or at most from the distance of the Moon, still close enough to see Earth clearly as a recognizable whole world. A traveler far out in interstellar space wouldn't have that option. Earth, from that distance, isn't a blue marble hanging in a window. It's an indistinguishable point of light, buried among thousands of other points of light, requiring careful calculation just to identify which one it even is. The very experience that has moved so many astronauts to describe a renewed sense of connection to home would, ironically, become unavailable exactly when a traveler might need that sense of connection most. The uncertainty we've discussed tonight isn't a fixed, unchanging number. It grows continuously, the entire time a spacecraft is traveling, spreading outward the way ripples widen on a pond, except in 3 dimensions, and without ever settling back down. At the start of a journey, position is known with excellent precision, calibrated carefully against Earth just before departure. A year in, small errors from dead reckoning, star drift, and instrument calibration have begun to accumulate, but remain relatively modest. A decade in, without frequent, precise correction, that uncertainty has grown substantially. It's no longer a tight, confident dot on a map, but a widening region of possible positions. Multiple decades in, deep into a genuine interstellar journey, that region of uncertainty could easily have expanded to a scale encompassing millions of miles in every direction. A fog of possibility rather than a single, known point. This is the fundamental shape of the entire problem we've explored tonight. Not a single moment of being lost, but a slow, continuous drift away from certainty, compounding quietly with every passing year. That happens regardless of how carefully each individual instrument was built or how skillfully each individual correction was calculated. There's a reason this particular challenge, more than almost any other aspect of interstellar travel, tends to get glossed over in popular imagination. Faster than light travel, artificial gravity, suspended animation, these are all dramatic, visually compelling problems with equally dramatic, imaginable solutions. Navigation, by comparison, feels mundane, a background detail rather than a headline challenge. But as we've seen tonight, it might actually be one of the most stubborn, deeply rooted problems facing any realistic vision of deep space travel. Not because it lacks a clever technological fix, but because it's tangled up with some of the most fundamental features of the universe itself. The absence of any fixed reference frame, the finite speed of light, the reality of time dilation, the sheer, overwhelming scale of the distances involved. Every other challenge in space travel, propulsion, life support, radiation shielding, is at its core an engineering problem. Difficult, but theoretically solvable with enough time, funding, and ingenuity. Navigation across true interstellar distances is partly an engineering problem too. Engineers will undoubtedly continue improving every tool we've discussed tonight: pulsar timing, star tracking, autonomous onboard systems, laser ranging. But underneath all of that lies something engineering alone can't fully resolve. A universe that was simply never built with a fixed address system in mind, where every location only makes sense relative to other locations that are themselves in constant motion. And that leaves us with a strange kind of humility. The same restless curiosity that makes us want to leave Earth, to cross the vast darkness and see what's out among the stars, runs directly into a problem woven into the basic structure of the cosmos, one that no amount of ambition alone can simply overpower. There's one last idea, a way researchers have suggested we might soften this problem, even if we can't fully solve it. Rather than trying to relocate Earth directly from across light years, a returning mission could instead aim for a pre-computed rendezvous point. That's a specific location and time agreed upon before departure, calculated using Earth's well-understood orbital motion, projected forward across however many years the round trip is expected to take. Instead of asking, "Where is Earth right now?" an impossible question to answer with any real-time precision from that far away, the traveler would instead be solving a narrower, more manageable question. Where will Earth be at this specific, agreed-upon future moment? That's a question orbital mechanics can answer with far more confidence, since planetary orbits unlike deep space drift, are governed by well-understood, highly predictable gravitational rules. This doesn't eliminate the problem. The traveler's own position still carries all the accumulated uncertainty we've discussed all night. The drifting gyroscopes, the shifting starlight, the fading radio contact. But it does shrink the size of the target, replacing a vague, ever-moving idea of home with a specific, calculable point in space and time, giving every layered, imperfect navigation method something more precise to aim for. It's not a perfect fix. It's a narrower, more forgiving version of the same problem. And in a universe with no fixed points to rely on, narrowing the problem down is often the most realistic kind of progress available. History actually offers a striking parallel to everything we've discussed tonight, one that unfolded centuries before anyone imagined leaving Earth at all. For most of the age of ocean exploration, sailors could determine latitude, their position north or south, fairly reliably by measuring the angle of the sun or known stars above the horizon. But longitude, position east or west, was a different story entirely. For centuries, it remained one of the most dangerous unsolved problems in navigation. Without a reliable way to measure longitude, ships regularly misjudged their position by hundreds of miles on long ocean voyages. It was a dangerous, sometimes fatal error that led to shipwrecks on unexpected coastlines and vessels running out of supplies while searching for land that wasn't where their charts suggested it should be. The underlying issue was almost identical, in principle, to the problem we've spent tonight exploring. Determining longitude required knowing the precise time at a fixed reference location, comparing it against the local time determined by the position of the sun, and using the difference between the two to calculate how far east or west a ship had traveled. The trouble was clocks. No timekeeping device of the era could maintain accurate time aboard a rocking, humid, temperature-shifting ship for months at sea. It would drift by minutes or hours over a long voyage, and a small error in time translated directly into a large error in calculated position. It took decades of dedicated effort and the development of an entirely new kind of mechanical clock specifically engineered to remain accurate despite motion, temperature changes, and humidity. Only then did reliable longitude calculation finally become possible, transforming ocean navigation and dramatically reducing the number of ships lost to simple positional error. The parallel to deep space navigation is almost exact, separated only by scale. Just as 18th century sailors needed an extraordinarily precise, stable clock to solve the longitude problem, any realistic interstellar mission needs extraordinarily precise, stable timing, whether from atomic clocks or pulsar signals. It comes down to the same fundamental challenge: figuring out a precise position using nothing but careful, patient measurement against a moving, imperfect set of references. It took roughly 40 years, and the dedicated work of an inventor who spent much of his life refining smaller and smaller, more and more accurate mechanical clocks. Only then was the ocean-going version of this problem finally, reliably solved. There's no reason to assume the interstellar version will resolve any faster. If anything, given the scale involved, trillions of miles instead of thousands, years of communication delay instead of weeks, it may well demand an even longer, more patient process of incremental refinement before anything resembling a reliable, trustworthy solution exists. Every spacecraft humanity has ever launched, no matter how far it's traveled, has remained, in some fundamental sense, on a kind of tether to Earth. It's a thin, patient thread of radio contact stretching across the growing distance, kept alive by an entire network of engineers, antennas, and carefully maintained infrastructure back home. Voyager 1. Even now, drifting through interstellar space, more than 15 billion miles away, still checks in. Its faint signal still reaches the giant dishes of the deep space network, still gets decoded, still gets logged, still gets answered, even if that answer takes more than a day to arrive. That tether is thin, strained by distance, weakened by time, but it hasn't broken. A true interstellar traveler, venturing far enough and staying gone long enough, would eventually reach a point where even that thin tether becomes meaningless. The delay grows so long, and the signal grows so faint, that Earth stops being a place you can meaningfully communicate with at all. It becomes instead a place you can only calculate toward, using nothing but memory, mathematics, and hope. So where does that leave us? If dead reckoning drifts, if starlight bends and shifts the faster you move, if pulsar timing, though promising, still carries its own uncertainties, if radio contact with Earth becomes a conversation with the past rather than the present, and if, even with a perfect fix on your position, the destination itself will have aged and moved on without you. The honest answer is that finding your way home from deep space isn't a solved problem. It's a layered one, made up of several partial solutions stacked on top of each other, each one narrowing the uncertainty a little, none of them eliminating it completely. Engineers today combine dead reckoning with star tracking with radio ranging from Earth, radio ranging with pulsar timing where possible, and constant correction whenever new data becomes available. For missions within the solar system, this layered approach works remarkably well, keeping spacecraft like Voyager and New Horizons precisely located even at staggering distances. But for a true interstellar journey, one lasting decades, crossing trillions of miles, moving fast enough for relativity itself to start bending the rules, every one of those methods weakens simultaneously. And no one has yet designed a system capable of holding all of them together with the precision such a journey would demand. Maybe someday that changes. Maybe future navigation systems will combine pulsar timing with new kinds of quantum sensors, capable of measuring motion and position with a precision we can't yet build. Maybe entirely new reference points, ones we haven't even considered yet, will be discovered, giving future travelers something steadier to measure themselves against. But right now, today, with the technology and understanding we actually have, the truth is simple and a little humbling. The farther you travel from Earth, the less the universe gives you to hold on to. Space doesn't offer road signs. It doesn't offer landmarks. It offers a handful of imperfect tools, a few clever tricks borrowed from centuries of ocean navigation, and an unforgiving amount of distance in every direction. Home isn't a coordinate frozen in space, waiting patiently for you to find your way back to it. It's a moving point, carried along by a spinning planet, orbiting a moving star, inside a moving galaxy, drifting through an expanding universe. By the time you'd worked out exactly where it used to be, it would already be somewhere else. And that, more than any single technical obstacle, is the real reason no one could simply turn around and fly home from deep space. Not because we lack the courage, not because we lack the ingenuity, but because the universe itself refuses to hold still long enough to let us. Thank you for joining me tonight on this exploration of one of the strangest problems in all of space travel. If you found this as fascinating as I did, please take a moment to like this video and subscribe to the channel. It genuinely helps this channel keep making these deep dives into the cosmos. And the next time you look up at a clear night sky, remember that every star you see is moving. Our own planet is moving. Somewhere out past the edge of everything familiar, home isn't a place you could point to. It's a moment that's already slipping away. Good night.